Welcome to Biogas Basics. My name is Jürgen Kube, and this is the fourth part of the mini-series about the gas system of biogas plants. In today's presentation, I will focus on how multiple gas domes on a biogas plant will interact with each other. I will show that without some kind of active gas management, all but one gas dome will become either full or empty during normal operation of the plant, and only one gas dome can actually be used to store biogas. I will present a simple method to manage gas domes and show an example how to manage the gas system of a biogas plant with multiple reactors. For more details, please see the publication listed below. Let's start with a very simple biogas plant. It comprises a primary and secondary digester. The total biogas production is 1000 norm cubic meters per hour. Under operational conditions with warm, humid biogas, this corresponds to around 1300 cubic meters per hour. The biogas flows from the primary to the secondary digester and from there to the gas consumers. Around 80% of the biogas is produced in the primary and 20% in the secondary digester. Under operational conditions, around 1040 cubic meters per hour flow from the primary to the secondary digester. The connecting gas pipe has a diameter of dn 250 and a length of 6 meters. The velocity in the pipe is 5.9 meters per second. We can now calculate the pressure drop of the flow in the pipe with the Darcy-Weisbach formula. Technically, it is for isothermal incompressible flow only, but the density changes of the biogas flowing through the plant are very small, so we can treat the flow as incompressible. The error is marginal. The pressure drop is proportional to half the density times the squared velocity times the sum of two terms. The first term covers the friction factor of the flow in the pipe. Lambda is the Darcy friction factor, here around 0.03. I have shown how to calculate the friction factor in the first presentation. L and D are the pipe length and diameter. The second term covers the pressure loss coefficients of confuser, diffuser, elbows, T-junctions, flaps and other fittings. The terms for confuser and diffuser alone add up to 1.5 when the pipes just stick in a tank. Don't forget these terms. In our example, the sum of all loss coefficients is 5. The pressure drop between the two tanks is 1.1 millibars. When we set up the gas domes, we can select the pressure in the first gas dome to 5 millibars. The second gas dome must be set to 3.9 millibars. Only if the pressure difference is exactly 1.1 millibars, the flow between the two tanks will be 1014 cubic meters per hour, equivalent to 800 norm cubic meters per hour when the gas has 50 degrees Celsius and is saturated. But what happens if we stop feeding for a while and the gas production in the primary digester drops from 800 to 600 norm cubic meters per hour? At first, the flow in the connecting pipe remains at 800 norm cubic meters per hour. Only 600 norm cubic meters per hour are produced in the primary digester, so the gas dome on the primary digester depletes with 200 norm cubic meters per hour. When a gas dome level drops, its pressure drops as well, so the pressure difference between the primary and secondary will reduce, leading to a reduced flow. However, this effect will only last until the gas dome on the primary digester is empty. A similar effect happens if the feeding is increased and the gas production in the primary digester increases to 1000 norm cubic meters per hour. The gas dome level increases until the gas dome is full. When a gas dome is either full or empty, its inner membrane will lay itself onto the outer membrane or the belt structure, and the restriction will take up some of the area force and allow the pressure in the biogas space to deviate from the pressure set up by the blower and pressure control flap. If the gas dome is full, the outer membrane projects a force onto the inner membrane and the biogas space can be overpressurized to provide a sufficient pressure gradient to push all the gas produced in the digester downstream. When the gas dome is empty, the inner membrane lies on the belt structure. The belt structure takes some of the area force produced by the air blower of the gas dome, and the biogas space can have a lower pressure than the airspace. Other effects that can cause a difference in the flow are temperature and corresponding density and humidity changes of the biogas, sulfur precipitation, or condensate accumulation in the gas line between the two tanks. The point is, it is impossible to precisely predict all factors affecting the required pressure drop between the two digesters. Therefore, the pressure in the two gas domes cannot be exactly set to correspond with both the interdigester gas flow and the friction coefficient of the connecting gas pipe. We need some kind of feedback controller for the pressure. If the biogas plant has two or more double membrane gas domes, use the following algorithm. Identify the gas dome with the highest operational pressure and control its pressure to a constant value with the pressure control flap and the variable speed drive of the air blower. Most of the time, this is the gas dome furthest upstream or with the highest gas production. All other gas domes will have a lower pressure. This gas dome is the main gas dome. It is the upper dome in the figure. Control the pressure in each other gas dome, which we term ancillary gas dome, with a bang-bang or two-point controller, so that if the level in the ancillary gas dome is lower than the level in the main gas dome minus a hysteresis, the pressure in the ancillary gas dome is at its lower pressure set point. This lowers the pressure in the ancillary gas dome slightly, and lets gas flow from the main gas dome into the ancillary gas dome, equalizing the two levels. If the level in the respective ancillary gas dome is higher than the level in the main gas dome plus a hysteresis, the pressure in the ancillary gas dome is controlled to its upper pressure set point. The higher pressure lowers the pressure gradient slightly, ensuring that less gas flows into the ancillary gas dome, again equalizing the two levels. Repeat individually for every ancillary gas dome. Each ancillary gas dome only compares itself against the main gas dome. The pressure controller can be a simple PI controller but should contain an anti-wind-up function, because the pressure in the ancillary gas domes will never reach the set point. During normal operation, the pressure differences between the main and ancillary gas domes will only be a very small amount, less than 0.1 millibar. The change in pressure difference cannot be measured, but it has an effect on the gas dome levels. This control algorithm will keep all gas domes at the same level. Biogas will be stored or unloaded slowly and equally among all gas domes, and the volume flows, and thus pressure gradients between the tanks are minimized. The gas consumers are also better controlled by the gas dome level, as low-level or low-pressure events in individual tanks that could trigger the release of the gas safety chain are avoided. Using pressure set points instead of fixed blower speeds adds an extra level of safety. Even if there is an unexpected error in the gas system, the pressures in the ancillary gas domes will always stay between their minimal and maximal limits. The method is covered by a European patent. If you want to use this method in a country covered by the patent, check licensing requirements and obtain a license if necessary. Here is the example biogas plant from the first part of this mini-series again. It has two CHPs. The first 1200 kilowatts CHP operates as baseload and provides high-temperature heat to an amine scrubber of a neighboring biogas plant. A second 1560 kilowatt CHP provides peak load during times of high energy demand in the grid. In this application, the plant must store and discharge biogas from the gas domes. First, I will show how the gas management algorithm works on a real plant. Then I will compare it with the calculated pressure profile using the pressure drop method for ring systems. The pressure gradient over the plant changes between charging and discharging, and the gas domes must be actively managed to make full use of the storage capacity. The first figure shows the gas dome levels, black for the main gas storage on the secondary digester, orange for storage tank 1, and purple for storage tank 2 on the right ordinate. The power output of the CHPs is shown on the left ordinate, red for the smaller CHP1 and cyan for the larger CHP2. The abscissa shows the time from 0 to 96 hours. We see that the main gas store level fluctuates and the levels of the two ancillary gas storages on the storage tanks follow the main gas storage. The levels in the ancillary gas storages are usually 2 hours behind the main gas storage, but do eventually catch up. The two ancillary gas domes have the same level within 1 or 2%. The plant can make full use of its gas storage. Now let's focus on the 12-hour window between 6 and 18 hours. The gas domes inflate in this period. This figure shows the gas dome levels again, but on the right ordinate are the frequencies for the blowers of all gas domes. Instead of controlling the pressure in the main gas store to a constant value, the speed is controlled to a fixed value, and the pressure is controlled by the pressure control flap. The speed of the blower for the main gas store is the black bold line. The blower runs at constant 50 Hz. The speed of the blowers for the storage tanks is controlled with a bang-bang controller and fluctuates between 48 Hz and 40 or 39 Hz, respectively. The fluctuation in blower speed leads to tiny changes in the headspace pressure, which forces more gas into or out of the ancillary gas domes and controls their level to the level of the main gas storage. This is the headspace pressure of all four tanks. The pressure in the primary digester with the concrete roof is the green line. We can barely see any pressure differences. The pressure in all tanks is more or less the same. The baseline fluctuates, but the pressure difference between the tanks is less than half a millibar. A low pressure gradient is not automatically the case for all biogas plants, but this plant has a ring gas pipeline and was designed to minimize its pressure gradient within the plant. Nevertheless, keep in mind that the pressure in all gas domes rises and falls together. In a plant without gas management, one gas dome will take the full gas accumulation stream if the gas consumers stop. The rapid increase of the gas dome level will lead to an increased pressure in the gas dome, as we have seen in the previous presentation. In this case, the pressure in all gas domes rises, not just in the gas dome that experiences the gas accumulation. All gas domes can vent in this occasion. We get a better idea when we look at the pressure difference between the main gas storage and the ancillary gas storages. I plotted the cumulative distribution function, or CDF, on the left ordinate. It is the sigmoid-shaped bold curve. Its derivative is the probability density function, or PDF, which is the bell-shaped dashed curve and is shown on the right ordinate. The abscissa is the pressure difference to the main gas storage on the secondary digester. The cumulative distribution function shows how often the pressure in the respective gas dome deviates by the value on the abscissa, and the probability density function shows the probability how often this is the case. On average, the storage tanks are 0.08 millibar below the pressure in the secondary digester, but the pressure difference fluctuates from minus 0.4 to plus 0.2 millibar. So occasionally the flow reverses and biogas flows from the storage tanks into the secondary digester. On average, at the median, the pressure in storage tank 1 is slightly lower than in storage tank 2, but the difference is basically unmeasurable, 0.02 millibar. We are getting close to the measurement accuracy of the pressure sensors. This shows that it is impossible to predict the pressure differences between the tanks a priori, and the system can only be stabilized with a feedback controller. To complete the example, let's calculate the average biogas flow for the loading and unloading scenario. This is the maximal load scenario. The flow to the gas consumers is 0, and the gas dome levels increase by 145 and 427.5 cubic meters per hour in the secondary and gas storage tanks respectively. In total, the average biogas production of 1000 cubic meters per hour fills the gas domes. The pressure in the secondary digester is controlled to 5 millibar. The pressure gradient over the plant flattens, because gas is stored in the gas domes and the outflowing streams decrease. The pressure difference between secondary digester and storage tank 1 is 0.16 millibar. Now we switch on both CHP and unload the gas storages. The flow to the gas consumers is 1380 norm cubic meters per hour. The gas domes on the secondary digester and the storage tanks deplete at a rate of 55 and 162.5 norm cubic meters per hour respectively. In total, 380 norm cubic meters per hour are discharged from the gas storages on top of the 1000 norm cubic meters per hour gas production. The flows in the biogas plant increase and the pressure gradient widens to 0.46 millibar between the secondary digester and storage tank 1. The pressure drop forecast is slightly higher than the measured values. The data were produced during the commissioning period when the gas pipes were still clean and had a lower pressure drop, but the gas management algorithm will compensate for increased pressure drops after commissioning. Let's summarize. Fixing the pressure in two gas domes enforces a defined flow between the two nodes. This follows from the Darcy-Weisbach equation for the pressure drop in pipes. The pressure drop is proportional to the square of the flow and constant pipe geometry factors. If the enforced flow is not exactly equal to the average flow based on the gas production in each tank and the gas consumption of the gas consumers, one of the gas domes will fill or deplete. Only when the gas dome is full or empty, the inner membrane can press itself against the outer membrane or belt structure, and the pressure in the biogas space can deviate from the air pressure. For multiple gas domes, only one dome can act as a storage. The others are always full or empty and cannot be used. In the best case scenario, and after careful setup, it might be possible to use some gas domes sequentially, but most of the time, the gas dome volume cannot be used fully as storage space. For the gas management algorithm, set the pressure in the main gas store to a constant value or operate the blower at constant speed. Control the gas dome level in the ancillary gas domes to the level in the main gas dome by varying the blower speeds or pressure set points. Repeat for every ancillary gas dome individually. When a gas management algorithm is implemented, all gas domes fill simultaneously and can be fully used. Pressure spikes that are generated by gas domes filling consecutively and led to venting or flaring are avoided. The example plant shows the successful implementation of the gas management algorithm. The measured pressure differences show that a pressure gradient cannot be enforced externally, but must be controlled with a feedback controller. This concludes part 4 of the mini-series about the gas system of AD plants. A gas management system is easy to implement, and a quick win for larger biogas plants with more than one gas dome. Even if it prevents only 1% venting, it has a high impact on the profitability and sustainability of a biogas plant. I hope you learned something new, and I see you in the next episode of Biogas Basics.